For the last 50 years, the rule for making computers better was pretty simple. Just make everything smaller, faster, and more powerful. But that relentless march, it's come to a grinding halt. And right at the moment the old rules broke, a new kind of demand, something of unimaginable scale, appeared on the horizon. It's forcing a complete revolution right from the silicon up. And just look at how fast things escalated. We're talking about going from billions to trillions of parameters in just a handful of years. This isn't just a simple increase, it's a total phase shift in what we're asking our computers to do. It's an absolute explosion of complexity that our technology was frankly never built to handle. So that's the big question we're going to tackle in this explainer. It's a story about hitting the absolute hard limits of physics and the incredible ingenuity it takes to smash right through them. Okay, let's dive in. For decades, the recipe for speed was easy, right? Just shrink the transistors and crank up the clock speed. Simple. But in the early 2000s, engineers ran into two problems they just couldn't shrink their way out of. Two fundamental walls made of silicon and, well, physics. The first one is called the memory wall. Now, the best way to get your head around this is with an analogy. Think of your computer's processor as this world-class chef who can prep ingredients at lightning speed. But the data, the ingredients themselves, they're stored in a warehouse a block away. So the chef spends almost all their time just waiting for deliveries. That infuriating delay? That is the memory wall.
And believe me, this isn't a small delay we're talking about. A modern CPU can do a basic operation in a fraction of a nanosecond. But fetching data from main memory, from the DRAM, that could take over 100 nanoseconds. That's a performance gap of more than 100 to 1. The processor is just sitting there, tapping its fingers, idle for like 99% of the time, just waiting. It's a massive, massive bottleneck. And the second villain in our story is the power wall. See, the old strategy was to just pump more voltage into the chip to make it switch faster. The problem? All that energy turns into heat. We got to a point where cranking up the clock speed, even a little bit, would generate so much heat that the chip would literally melt itself. So the takeaway here is simple. The old playbook was done. It was finished. We couldn't just brute force our way to faster computers anymore. We had to get smarter. And this is where our story splits into two really fascinating paths. First up is Apple's radical bet to solve that memory wall. Their idea? Instead of trying to make the delivery truck faster, they decided to completely redesign the entire kitchen. So, on the left, you've got the traditional PC architecture. It's this big, sprawling system. The CPU is over here, the graphics card is over there, and the memory sticks are in their own slots, all connected by these relatively slow electrical highways. But on the right, that's Apple's M-series architecture. It's a system on a chip, an SoC. The CPU, GPU, neural engine, and, this is the crucial part, the memory, are all baked together into a single tightly integrated package. This whole thing is what they call unified memory architecture, and it is a direct assault on the memory wall. So to go back to our chef analogy, they basically put the entire kitchen, the fridge, the pantry, the chopping board, right next to the chef. By putting the memory physically beside the processor on the same piece of silicone, everything is within arm's reach. The data is right there, ready to go instantly.
And the results? Well, they speak for themselves. The M1 Pro hit over 200 gigabytes per second of memory bandwidth, a number that was just completely out of reach for regular desktop computers at the time. And then with the M1 Ultra, they pushed that to over 800 gigabytes per second. This is the direct payoff of that integration, a fire hose of data available instantly to every single part of the chip. So, Apple's integration strategy was a huge leap forward, no question. But just as the industry was grappling with this new approach, the problem itself changed. The absolutely insane computational demands of modern AI showed up, creating a challenge of an entirely different magnitude.
Okay, so to really get this new challenge, you have to understand the two main phases of AI. First, there's training. This is like teaching the AI model. It's incredibly expensive, computationally speaking, done on huge batches of data, and it needs really high precision. Then there's inference. That's you actually using the AI to get an answer. And that has to be incredibly fast, right? You don't want to wait 10 seconds for a chatbot to reply. It turns out you can also use less precise math here without really affecting the result. The key is these two jobs are fundamentally different, and they demand totally different kinds of hardware.
And that need for specialized hardware? Well, that brings us to the second major path in our story, the rise of the AI titans, NVIDIA and Google. They took a different approach. Instead of a do-it-all integrated chip, they started building hyper-specialized accelerators designed to do one thing and one thing only: the massive matrix math that underpins all modern AI.
NVIDIA's strategy is basically to provide overwhelming, flexible firepower. Their GPUs, like the H100 and the new Blackwell platform, are just packed with thousands of specialized processing units called tensor cores. These are designed to do one thing exceptionally well, that specific matrix math that's the backbone of AI. You pair that with massive amounts of high-bandwidth memory, and they become like a Swiss Army knife for AI. Incredibly powerful, super adaptable, and that's why they dominate the world of AI training.
Google, on the other hand, took an even more specialized route with their Tensor Processing Unit, or TPU. And at the heart of the TPU isn't a general-purpose processor at all. It's a very specific piece of hardware called a systolic array, and it's a completely different way of thinking about computation.
To understand this, just think of an assembly line. In a systolic array, data flows through this grid of processors in these rhythmic waves, kind of like a heartbeat. Each tiny processor does one simple little calculation and immediately passes its result to its neighbor. Now, it's not flexible at all, but for that one specific task that dominates AI, matrix multiplication, it is unbelievably, incredibly efficient.
So what you're really seeing here is a clash of philosophies. On one side, you've got the NVIDIA GPU, the powerful generalist. It uses a more traditional setup with thousands of cores and a cache system, making it great for a huge range of AI training and other high-performance tasks. And on the other side, you've got the Google TPU, the hyper-specialist. Its systolic array and software-managed memory are fine-tuned for one thing, efficiently running these massive-scale AI workloads where performance is predictable.
So how much does all this specialization really matter? Well, for some jobs, the difference is just staggering. A highly specialized chip like Grok's language processing unit, which takes that deterministic assembly line idea even further, can be over 18 times more energy efficient than more general hardware. That's not just a small improvement, that is a complete game changer. It proves that for the future of computing, one size definitely does not fit all.
And all of this brings us to the new reality of computing. The era of the single, all-powerful general-purpose processor, it's over. We've seen two successful but very different paths forward. Apple's deep integration on one hand, and the AI titans' targeted specialization on the other.
So, what does this all boil down to? It's a fundamental shift. We've moved from a world where we tried to build the fastest generic chip possible to a world where the specific software problem now defines the hardware solution. Getting data to the processor, the memory system, is now the single most important part of the design. And that choice between integrating everything like Apple or specializing for one task like Google, well, that's the fundamental trade-off that's going to define the next generation of all our devices.
Which leaves us with a pretty fascinating final question to chew on. Apple's approach gives us a powerful, unified brain, capable of doing a lot of things very, very well. The AI specialists, meanwhile, are building a society of experts, where each one is phenomenal at its one given task. As AI gets more deeply embedded in every part of our lives, which model is going to win out? The versatile generalist or the hyper-efficient specialist? The answer to that is going to shape the future of technology itself.